Okay. Okay.
Yeah, it's okay.
So it's a pleasure to present Leonor Silvestre. She's from Instituto Superior Técnico, Universidade de Lisboa, Portugal. And it's a coincidence, but tomorrow is the day of the woman and girls in science and technology. So it's a very good way to recall everybody that here we are, the woman. So she's going to talk about optimal boundary control for drag minimization in a fluid rigid body interaction. Thank you, Leonor.
Thank you very much for the introduction, and thank you very much for the invitation. It is a pleasure to give a seminar in this webinar Control in Times of Crisis. I am going to present a joint work with Toshiaki Ishida from Nagoya University in Japan and Takeo Takahashi from INRIA Nancy in France. Okay, so first I am going to give the formulation of the problem. This fluid structure interaction problem is a very special one in the sense that the problem is going to be formulated in terms of an exterior Navier-Stokes problem coupled with the equations of a rigid body which is moving within this Navier-Stokes liquid. I am going to show the derivation of the equations. In particular, we worked with the steady state counterpart of this fluid structure interaction problem, and then I am going to formulate the control problem. Since this is an exterior problem, we are going to need to understand very well what is the asymptotic behavior of the Navier-Stokes solutions, because this is going to be important not only for the analysis of the direct problem, let's say, but also for the formulation and for the solution of the control problem. After we have all these framework very well established, and once we have the well-posedness for the solutions of the coupled Navier-Stokes liquid equations and the rigid body equations, we are ready for the study of the optimal control problem. And what we want is to reach a certain target velocity for the rigid body, and at the same time to reduce, to minimize the drag that is associated with the motion of this rigid body. So we are going to give a suitable formulation for the control problem, in particular for the cost functional. Then we show existence of solutions for the state equations. Not to show, but let's say, yeah, okay, we show existence of solutions for the state equations, because here in the first part of the talk, it is just the formulation of the problem. Then we show existence of optimal controls, and finally, we give a characterization of the optimal controls, namely, we are going to present the adjoint equations and the first order optimality condition. Okay, so concerning the formulation of the problem, we are going to be interested in a very special fluid structure interaction problem. So what we have here is what is called a self-propelled motion. So this means that we have a solid body, which is a rigid body moving inside an Navier-Stokes liquid. And since this rigid body, by definition, cannot deform, it means, and we are also going to assume by the definition of self-propelled motion, that there are no external forces acting on the rigid body and also on the liquid. This means that there has to be some mechanism generated by the rigid body itself that is going to cause the motion of the rigid body. So we can give the following definition. A rigid body undergoes a self-propelled motion in a certain fluid F if the external force acting on the fluid is identically zero, and if the total force, the total net force and torque external to the system solid fluid, which is acting on the solid, is also zero. Let's see how this can be expressed in terms of equations. I have here, let's say, a classical example, which can be a submarine moving in the sea, but also the motion of certain microscopic organisms like cilia can also be modeled as a self-propelled motion of a rigid body. These microorganisms, since they are very small, we are not able, let's say, to see their deformation, and they will move because they have a kind of hair in their surface, and they move it. So this also helps for the motion of these microorganisms. So let's see in terms of the equations. If, for instance, we had a fish swimming in the sea or in a river, in that case, we should consider the deformation. So in that case, we should not model this as a rigid body. Okay, so let's start with the equations of the liquid, but we are start with the formulation of these equations in an inertial frame. Okay, so we are fixed in a certain reference frame, and we are observing the rigid body that is moving, and also the motion of the liquid that is due to this motion of the solid. So what we have here is, first of all, a fluid domain that is going to be dependent on time, okay? And what we have here is the conservation of linear momentum for the velocity and the pressure, okay? The tensor that appears here is the classical one associated with a Navier-Stokes liquid. So we will denote by D of U the symmetric part of the gradient, and here Q is the pressure. Okay. At this stage, I am going to denote the pressure by Q. So it's a small mistake here. Here should be Q instead of P. We are going to consider an incompressible fluid, so the divergence of the velocity is zero. And now, since we are in an exterior domain, we also have to say something about the asymptotic behavior of the fluid. So at this point, what we say is that very far away from us, the fluid is, or very far away from the rigid body, the fluid is at rest. Okay. Then, of course, for the analysis of the equations, we will have to be more precise about how this limit is going to be equal to zero. Okay. Since at first this is a problem dependent on time, so here we are also going to consider some initial condition for the velocity. Okay, so we are writing the first equation in divergence form, but the divergence of sigma of U and Q means, because of the divergence free condition, that we can write viscosity times the Laplacian of U minus the gradient of the pressure. Okay, the velocity is a vector field, the pressure is a scalar. Now, what we have is the Navier-Stokes equations around a rigid body, and the velocity field for a rigid body can be written in the form that I have here, the last equation. This is the translation of the center of mass. YC of t is the position of the center of mass of the rigid body, and in this first set of equations, theta of t is the angular velocity, which is also a vector. Okay, so now let's see what are the boundary conditions in the interface between the solid and the fluid. So since since the rigid body is moving, we also have to account for the velocity of the rigid body, since we want some continuity on the velocity of the fluid. And then if we remember what we said before about what causes the motion of the solid, of course that there is an interaction with the fluid, but there is also some mechanism that is developed by the rigid body itself, and we are going to denote it by U star. Okay, so the rigid body is going to move because it generates itself some distribution of velocities on its boundary, like for instance is shown here. Okay, in the case of the submarine, we can assume that, for instance, this propeller that is here, of course it is moving, but somehow we can associate this this velocity with something that is generated here. Okay, so now the equations of motion of the solid. Again, in this inertial frame, what we see, so this is, I am recalling here the equations of motion of the solid, and now we have to take into account for the motion of the solid that there is the interaction of the solid with the liquid, and there is some force that is exerted by the liquid on the surface of the rigid body. So these are the Newton laws for the motion of the solid, and here we have the acceleration associated with the translational velocity of the center of mass. This is the total force exerted by the liquid on the boundary of the rigid body, and this is some net moment flux that is due to the existence of this distribution of velocities on the surface of the rigid body. Then we have another equation for the angular momentum, and here we have the angular velocity. Okay, and we have here also the inertia matrix of the solid, which in the case when we are describing the motion from this inertial reference frame, this matrix is going to depend on t. Okay, and we have to append here some initial conditions. What we have here is the torque associated with this force, and here we have the torque associated with this force. Now, since we have only one rigid body and we are in an exterior domain, it is possible by means of a suitable change of variables to make the fluid domain time independent. So what we are going to do is to consider a reference frame that is attached with the rigid body. So the origin of this reference frame is going to coincide with the center of mass of the rigid body, and then we are able to write the Navier-Stokes equations in a domain which is known and is independent of time. This is good for us because we don't have, because before the domain was also an unknown in the problem, and now it is not anymore. So this is good, but we pay a price with this, which is the following. Due to this change of variables, we are going to have extra terms in the Navier-Stokes equations. Okay, so here we have a Coriolis force, and here we have a term that in part we know, for instance, that we know when we study, let's say, the Ozin equations. This also appears. In this term here, this is the new velocity of the rigid body in this new reference frame, and this term here can be written like this in terms of the transformed translational and angular velocity of the rigid body. And this term we know more or less well from the Ozin equations, but we have another term here that is not so pleasant because we are in an exterior domain, okay? And we have here something that is, this function here is going to be unbounded, okay? If we were in a bounded domain, this would not be a problem, but in an exterior domain, this is going to cause some extra problems, okay? So this is the formulation of the Navier-Stokes equations in the reference frame that is attached to the solid. Now, by means of the same change of variables, we have now this new formulation for the equations of the rigid body. Okay, we have here, for instance, these new nonlinear terms that are due to this change of variables. This m is the mass of the rigid body, and now this y is a matrix, is the transformed inertia matrix, which now in this reference frame that we are considering in this new formulation is independent of time, and it is also symmetric and positive definite. Okay, so let's put everything together, and our fluid rigid body interaction problem is described by these equations. So here, which are our we can consider several problems associated to these equations. So let's say that the classical fluid structure interaction problem is the problem in which we know this V star, we know the mass of the rigid body, we know the inertia matrix, and we want to find the velocity and the pressure of the fluid, and we also want to find the velocity of the rigid body, okay? Now, the equations, in this case, the equations are coupled through the boundary conditions, because in the classical, in the direct fluid structure interaction problem, this capital V, namely this function C of t and omega of t, these are unknowns, okay? And so we have an unknown here on the boundary condition, okay? And also here on the Navier-Stokes equations, okay? So there is a coupling by the boundary condition, and also by these extra terms in the Navier-Stokes equations. Now, since we have these extra unknowns compared to the usual Navier-Stokes equations, we need extra equations for finding them, and actually, of course, we have here the equations of motion of the rigid body, okay? So this is a set of three equations, three ordinary differential equations. This is another set of three ordinary differential equations, okay? So chi and omega are unknown, but now again we have here the coupling with the fluid by means of the velocity and the pressure, okay? And here we have again our unknowns chi and omega, okay? If we want to solve this, we can consider, let's say, some functional spaces where we can put on the boundary of omega a general rigid motion, and we can solve this coupled set of equations, for instance, by Galerkin method. This would work. There are some difficulties associated with the fact that we have a coupling, but also we have an exterior domain. But the problem of finding the velocity, the pressure, chi and omega can be solved by Galerkin method. Now, in our case, what we are going to consider for the control problem is the steady counterpart of these equations. So what we are going to do is to consider a steady motion described in the reference frame attached to the rigid body. So we are going to assume that the time derivatives are not in the equations. We also discard the initial conditions, of course, and we consider the steady states described by this set of equations, which could again be solved by Galerkin method in these functional spaces where on the boundary of the fluid domain we put very general rigid body motions. Okay. Now let's see what we are going to consider for our control problem. In our control problem, we are going to consider two different types of controls, also taking into account certain problems that we find in real life. So again, let's recall that the motion of the rigid body is due to this distribution of velocities v star on the surface of the rigid body. And we are going to consider self-propulsion, what means that in two different situations that are common in real situations. A first one is the case where we have this velocity v star concentrated only on the part of the boundary. Okay, so in this case, the motion of the rigid body is due to essentially to this integral here. Okay, to a moment to this net flux of momentum across the boundary, and the velocity v star is going to be zero on a part of the boundary. This means that these velocities v star are going to be concentrated in a portion that we are going to denote by gamma. Now, another situation that we are interested in is the case of a rigid body moving, for instance, by a kind of belts on its surface, and in this case, this v star is tangential to the boundary. Okay, so we have v dot n equal to 0, and these integrals here are going to disappear in the equations. Okay, somehow this is good for us because the equations are going to be a little bit lighter. Okay, so we are going to consider these two types of controls in our problem. So I am just recalling here what is, let's say, the direct fluid structure interaction problem. So it's a problem described by this set of equations in which we know v star and we are looking for the velocity for key and omega, and also for the pressure, as I said before. I am going to take this opportunity here to just to recall that, for instance, if we are considering tangential boundary values, okay, as the generator of the self-propelled motion, these terms here are going to disappear and the equations become a little bit simpler. But still, v star is here on the surface of the rigid body. Okay, so I am going to start with some references that inspired our work. This formulation of self-propelled motion in terms of something formulated systematically in mathematical terms, it appeared in the paper of Giovanni Paolo Galdi about self-propelled motion of a rigid body in 1999. There are other control problems associated with the classical Navier-Stokes equations. This work here by Fursikov, Gansburger, and Hu, it's about optimal control for the time-dependent Navier-Stokes equations in the 3D case. That is also the case that we are considering here. And again, here the main difficulty was due to the exterior domain, and also to the characterization, to a very precise characterization of the boundary values that the authors used in this paper. Concerning, so here the authors were also interested in drag minimization. Still about drag minimization, there is also this other paper. Here it's a bounded domain, and here the control is also concentrated on the part of the boundary in this paper of Luca Dede. Still about control, but with a somehow different approach. I would like to mention this paper of Samartin, Takahashi, and Tuxnak. They somehow simplified the problem or reformulated the problem based on suitable assumptions as a Stokes problem, and somehow this allowed them to make a very nice study of exact controllability of this system. What I am going to present in this talk is a joint work, as I said before, with Toshiaki Ishida and Takeo Takahashi. First, we studied a problem in which the control was finite dimensional that we also need for the optimal control problem, and I am going to basically show what were the results that we obtained for the optimal control problem. Okay, so what we want is to propel the rigid body with a given target velocity. Okay, so now for the control problem, this capital V, this rigid body velocity is given. So we know chi and omega, and we want to find the distributions of velocities V star that are going to propel this rigid body until it reaches so that it reaches this target velocity, and at the same time we want to minimize the work that is needed to overcome the drag that is exerted by the fluid on the solid. Okay, and this work is given by this expression here. Okay, so here we have the stress tensor, and this is the velocity of the fluid on the boundary, which is the common boundary of the rigid body and the fluid. So we want to minimize this quantity, and we want to reach this rigid body velocity. Okay, so let's recall, this is our drag functional. These are our state equations, where now chi and omega are known and V star is going to be the control. The problem that we have here is the following. First of all, so we have, in fact, we have several problems that, let's say, we have to consider when we look at the problem formulated just in this form. First of all, we would like to have some kind of quadratic cost functional, which is much more pleasant to work in the control problem. And then we have to find some way to satisfy also the self-propelling conditions. So this is a set of 6 equations, okay, that have to be satisfied, and we have to take that into account when we are going to say what is going to be our V star, because now the self-propelling conditions are not going to be satisfied by means of the velocity capital V of the rigid body, because now this is known. Okay, so what we are going to do, I will explain this after some slides, but okay, I am going just to prepare for what we are going to need. So in fact, this V star is going to be decomposed in a part that is going to help us to also to account for these 6 equations, and another part that is going to be our control. Okay, so still we will have to understand very well our state equations, and in particular the Navier-Stokes equations. So the Navier-Stokes equations, as I said before, we have, if we disregard here the nonlinear term, the usual nonlinear term in the Navier-Stokes equations, what we have is a kind of generalized Ozin system. And when we are working in an exterior domain, since most times we solve the Navier-Stokes equations, for instance, by means of a fixed point approach, in which in the first step we can assume that this non-linear term is fixed and given, we will have to understand very well the mathematical properties of this generalized Oseen system. So here we are imposing that the fluid is at rest very far away from the rigid body. So this means that the velocity is going to zero very far away from the rigid body, but we will need to have a more precise information about the way the velocity is going to zero. So because of this, let's start by the study of the state equations, and in particular, let's start with the study of the linearized equations associated with the Navier-Stokes equations, which is can be called a generalized Oseen problem. So the classical Oseen problem is described by this set of equations. Okay, this is the usual term in the Oseen equations. We can also consider here some external force and some velocity on the boundary. So this is usually a problem also in the exterior of. In this case, it's only a translating rigid body. This force here, usually when we study the Oseen problem, we make several assumptions on the external force, and many times we make the assumption that the external force is the divergence of a tensor of this form, because then we are interested in applying the results to the Navier-Stokes equations. The problem that I am solving here is a three-dimensional problem, but many times when we are observing a river, for instance, and here I have the picture of a duck in a river, what we observe is that when the duck is moving, there is this region, the formation of a region behind the duck in this case, and this is called the wake region. And what we see here is some anisotropic behavior of the velocity. Okay, I have this 2D picture, but in the 3D case, we also have this wake region behind translating rigid body. So what we are interested is in understanding, first of all, what is the precise rate of decay of the velocity, for instance, in this region here and also inside the wake region. And it is going to be different. So what is known is that inside the wake region, the velocity is going to decay like 1 over modules of x. It goes to 0 like 1 over modules of x, but outside it is going to decay faster. So let's recall how is this decay, okay? This is also for the 3D case. So the non-uniform decay of the velocity is described, we can consider this weight function. We have here the 1 over the modules of x that somehow appeared here, okay? But then we also have this other term, okay? This function here depends on the translational velocity of the rigid body. If this is 0, the velocity is going to decay like 1 over modules of x. Okay, so this weight is going to appear in the estimate of the velocity like 1 over it's like an w. Okay, so in the Stokes case. So let's suppose that we have some object, and this object is fixed. So in this case, this term here will not appear, and it's a Stokes problem. In the case of the Oseen problem, we have a better decay. This term is always greater or equal than 0. We have a better decay, which is due to the translational velocity. Okay, the wake region that we see here in the 2D case can be described in terms of this function S with something like this. Here we put 1, but eventually we could put another constant, okay? Okay, so now we are ready for a more complex problem, which is the generalized Ozin system. Why is it a generalized Ozin system? Because we also have the present of the angular velocity. So in this case, the body is translating and is also rotating. And the effect on the, let's say, on the flow profile is also going to be different, okay? So let's see. There will be a combined effect of translation and rotation, which can be expressed now by this weight function. So the velocity is going to be controlled by a certain constant times 1 over W, and now in terms of rotation, we are going to have this effect on the decay of the velocity. So for instance, if translation and rotation are orthogonal, then this term here is going to disappear, and it's like we only have, let's say, a Stokes flow, okay, when we are in the linearized case. And in this case, we don't have the formation of the wake. If omega is, the angular velocity is different from 0, and it is not orthogonal to the translation, then there is this wake region, and the width of the wake region are going to depend on the angle between chi and omega. So when then we consider the Navier-Stokes equations for small data, in particular for small velocity, angular velocity and translational velocity of the rigid body, we can expect that we are going to have a similar behavior in the Navier-Stokes equations. Okay, this is what we can show for the generalized Ozin problem. So let's assume that we have some external force in divergence form, which is in L2, for instance, and also which has a decay described by the weight function that I showed before. If the boundary data is sufficiently regular, then for the generalized Ozin system, we have a unique solution, which has first derivatives in L2, second derivatives also in L2, and the pressure is in L2 with first derivative in L2. The velocity is going to decay like 1 over the weight function defined by chi and omega, okay? And we have these estimates that are going to be very useful for us because we will need to solve the Navier-Stokes equations by a fixed point argument, and we will need these estimates, okay? So in order to obtain these estimates and to have this constant independent of chi and omega, it's also useful to assume that they are bounded. So now, since we have the extra self-propelling conditions, and in particular due to the first self-propelling conditions, we are going to have another property that is very useful and it's very nice, which is the finite energy of the fluid is finite. And this is very interesting because usually when we are working in an exterior domain, we don't have the velocity of the fluid in L2. In particular, for instance, we lose Poincaré inequality when we are in exterior domains. But here, the first self-propelling condition which we can write more or less in this form, okay, if we want to compare with the Navier-Stokes equations, if this self-propelling condition, we can call it like this, is satisfied, so this term is equal to 0, then the velocity is going to be in L2. Okay. In this case, it is also useful for us to have an estimate on the L2 norm of the solution of the generalized Ozin problem that then we are also going to adapt for the Navier-Stokes problem. But for the generalized Ozin problem, we are able to get an estimate for the L2 norm of the velocity in terms of the gradient of the velocity and the L2 norm of the pressure. And also we have here the external force, okay, that then is going to be the nonlinear term of the Navier-Stokes equations. What we have here is the flux of the velocity on the boundary. Okay, this is a very technical result that we obtained by means of Fourier transform. First, we had to extend the problem to the whole space, and we were able to obtain these estimates. Okay, let's now talk about the optimal control problem, because now we have all the functional spaces and inequalities and properties of the let's say of the state equations that we need to reformulate the control problem and to solve it. So these are the state equations. Okay, so let's recall that our target velocity is the velocity of the rigid body. Okay, K and omega in this case are known. The control is V star. Okay, we also will have to solve for the velocity and the pressure. Okay, this is the mass, which is given, is known. The inertia matrix is also known. Okay, as I said when I was introducing the equations, since now this capital V is given, we will have to consider some extra unknowns that allow us to satisfy the self-propelling conditions. So we have not only we want to find this control associated with the Navier-Stokes equations, but still we have to account for some extra, let's say, unknowns to satisfy the self-propelling conditions. Okay, how we are going to do this? We are going to introduce six, let's say, a finite dimensional control space, which has dimension 6, which is exactly the number of equations that we have here. And let's see how do we construct the basis, let's say, of this finite dimensional space. Let's consider associated, let's say, with the generalized Ozin problem. Let's consider a generalized Ozin problem in which the velocities that we have on the boundary of the rigid body are the basic rigid motions. So this is the basic translation, this is the basic rotation, okay? And this is given, so this is a classical generalized Ozin problem with zero force, external force, and only the basic rigid body velocities on the boundary of the obstacle, okay? And now we are going to recall what is the tensor sigma that we have used before. This is the symmetric part of the gradient. This is the pressure. And we are going to consider some velocity fields that we are going to denote by GI and capital GI, which are the stress tensors, okay, associated with these basic fields, okay? And we are going to define the finite dimensional control spaces in the case of localized boundary controls and tangential boundary controls that we have mentioned in the introduction of the model, let's say. So the first finite dimensional control space is the space that is spanned by a function that somehow this is a kind of characteristic function that concentrates the control on a certain part of the boundary, okay? And these are these velocity fields that appear here. And in the case of tangential boundary controls, we are going to take these velocity fields and we are make the cross product with the normal. This is the exterior normal, exterior with respect with the fluid domain, okay? And these are tangential boundary velocities, okay? So now what we can do, in order to satisfy the self-propelling conditions and taking into account that we can solve the Navier-Stokes problem by a fixed point argument, what we do is, let's consider a generalized Ozin problem. Now, also considering some coupling with the equations of the rigid body, and let's put some force here, where we will see after the nonlinear terms of the Navier-Stokes equations. let's assume that now we have some velocity that is given here also. And let's try to satisfy these equations, the equations associated with the motion of the rigid body, by putting here 6 unknowns. So this will be the boundary values that we will put in the case of localized controls. This is the boundary values that we are going to put on the boundary in the case of tangential boundary values. And what we are going to do is these alpha I and beta I that appear here, they will be 6 equations, 6 unknowns that will help us to account for these 6 equations, okay? Because now this is given, this is also given, but still we have to satisfy these equations, okay? So let's see how we do this. We also consider this auxiliary problem, where we put the external force and the part of the boundary values that are given. And now we can solve this kind of finite dimensional control problem or inverse problem by writing it in terms of a linear algebraic system with 6 unknowns, which are the alpha and the betas that we have seen before. The form of this matrix, so this matrix can be written in terms of the fields that we have, of the velocity fields that we have introduced before, okay? And this allows us to solve a linearized version of the fluid structure interaction problem, let's say, in which the velocity of the rigid body is known, but there is some part of the velocity on the boundary that has to be unknown to account for the self-propelling conditions. What we can show is that the matrix that appears in this problem is symmetric and non-negative, okay, and in particular is going to have some, is going to be invertible if we are not very far away for the matrix that is associated with the Stokes version of this problem, okay? So here we have to make sure that we are not very far away for the Stokes problem, and this means that we have to assume that the translation and the rotation that we are prescribing are not very large, okay? In this case, we are able to solve this kind of finite dimensional control problem. Okay, this is the form of the matrix A in the case of tangential boundary values. So this is a very, the results are very technical, the notations are very heavy, but okay, this is, I think it's, in some cases it's necessary to show all these auxiliary results and all these formulas. Okay, so the states equations that we are going to consider now are the following. So now V, capital V, the velocity of the rigid body, the target velocity is known. So here V is known, omega is known, also here, okay? In a first step, to study the state equations, we also assume that V star is known, but to satisfy the self-propelling conditions, we have to put here some unknowns. And these unknowns are going to be on these finite dimensional control spaces that we have introduced here. So that's why we needed these auxiliary results in these finite dimensional control spaces, because we have to account for these 6 equations here. So in the first step, we are going to solve for V, P, and this finite dimensional control, okay? So this is what we are going to consider for admissible boundary velocities, let's say, and we can show that if our domain is of class C3, then there exists constants such that if the data is sufficiently small, and this is the data that you have that we have in the state equations, then we have the following result. We are able to find a solution to the coupled equations. A solution is a velocity for the fluid, pressure for the fluid, finite dimensional controls to account for the self-propelling conditions, and we will find a solution that decays like 1 over omega. Remember this from the generalized Ozin problem. And in this case, we are also going to have, so notice that here we have written the velocity in W22, because since it is a self-propelled motion, we have this nice property that the velocity is also in L2. And we have these estimates for our problem. So the weight function that describes the decay of the velocity in a first step is given by this. Then this can be somehow improved because we are still able to show that the velocity is in L2. Okay, so given this, let's see something else that we also can show using the information about the more precise asymptotic behavior of the velocity. Because, for instance, if we want to show the energy equation associated with this flow, it is not enough, since we are in the exterior domain and we have to do integration by parts, it is not enough just to say that the velocity decays to 0. We need to have more precise information about the decay of the velocity. And integrating by parts, we are able to obtain the energy equation. Now, why is the energy equation useful for us? Because in particular, we can simplify our cost functional using the energy equation, okay? So let's see how we can do that. Let's recall the form of our cost functional. And as I said, it would be nice to have something that could be written in terms of some quadratic terms, let's say. Okay, let's use the energy equation and let's replace this so that we obtain this expression here for our cost functional, okay? And here we have the velocity of the fluid, we have the control, and we have the finite dimensional controls that are not going to be associated with the control that we are going to obtain by the techniques of optimal control, but this V star C is going to be associated with the velocity that, let's say, is associated with the state equations, okay? So these are not going to be considered for the optimal control design. These are a kind of correctors for the control that have to be included in the state equations, okay? So they are of this form. So what we can show now, I will not show all the details, but we can show that if the admissible set of controls is composed of bounded functions V star, then we can show that if K and omega are also sufficiently small, then each of the optimal control problems, tangential controls or localized controls, admit a solution. What we can show now, so some of the estimates that we obtained before are very useful to show the existence of optimal controls. Now we want to characterize also the adjoint states, and we want to give a first order optimality condition. So to do that, let's consider a Lagrangian associated with the problem. Here I am going to show partial results for the tangential case, because in the localized case the equations are very heavy, okay, it's better to show just this case, because there is one term. There are some terms when we have V star dot n in the self-propelling conditions that are going to disappear and things become a little bit lighter. So this is the space where we have our, let's say, state velocity, okay? We know that the velocity is in W22. we can consider this decay if we have to consider some decay, and it is divergence free. Now, this space U is a space that we are going to consider for Lagrange multipliers, and the same for this space Z. So what we are going to do here is, there are those difficult terms that appear in the Navier-Stokes equations. We are going to need some ability for them, because we are going to multiply the state equations by some function U in this space capital U, and we will need to do integration by parts and so on. So it will be useful for us to put in this space of Lagrange multipliers this extra property, okay? And also we are going to say that on the boundary of the fluid domain and of our rigid body, these functions U are going to be generic rigid motions, okay? Generic rigid body motions velocities, okay? So the Lagrangian that we obtain in the tangential case takes this form, okay? So this comes from the cost functional, and this is obtained by multiplying the state equation by a function U in the previous space, and this other term here is obtained by imposing the boundary condition in the state equations. The adjoint system is obtained by taking the Gateau derivative of the Lagrangian with respect to the velocity of the field and with respect to the correctors of the control that we introduced before, which are those functions in the finite dimensional control spaces. Okay, so what we find is the adjoint system in this form. This first part here, okay, except for the terms associated with the rotation of the rigid body, and here is also included the translation. This is more or less known from the Navier-Stokes equations, the same with the divergence-free condition. Now, what we have here that may be new is this kind of boundary condition in the control space, which comes from what we have to put here, what we have considered here in this Lagrange multiplier space, okay? This is associated with the boundary condition. Okay, now the first order optimality condition. This is also a very technical part of our results. I am just going to show the form of the first order optimality condition, which is obtained also considering a study of the control to state mapping. Okay, the cost functional can be written in terms of a composition of the Lagrangian in this state in this control to state mapping. Okay, and we can take the derivative of the cost functional with respect to the control, and we find this expression. This is also very technical. And then we can so until now, it was not important, for instance, to have the velocity in L2, the velocity of the fluid, but here there is one part of our calculations when we use this result, okay, and when we take the Gateau derivative, and we have to take some limit when this parameter h goes to 0 in order to find the Gateau derivative. At some point, it is important for us to consider the L2 norm of the velocity fields, okay? And what we find in terms of the first order optimality condition in the case of tangential controls is this condition here, okay? So a characterization of our optimal controls. In the case we have small velocities of the rigid body, and also the controls are sufficiently small, okay? We can say that if V star hat is a solution of the optimal control problem with associated velocity pressure and finite dimensional and correctors of the control, let's say, with a corresponding solution of the unjoined system, then we have this first order optimality condition. And I am just going to show which are the form of the optimality condition when we consider localized controls. It is going to be a little bit more complicated because we have to account for these terms here, because in this case we don't have a tangential velocity. So basically this is the end of my talk, and thank you very much.
Thank you very much for your interesting talk. Are any questions or comments? Please open your microphone if you want to say something. No? Okay, I have a question. Enrique,
Okay.
You're going to talk? No, please, go ahead.
No, thank you very much. Very nice talk.
Thank you.
And I have no question.
No? Okay, I have a question. As I understood, you're acting for your optimal controls, you're acting on all the components of the Navier-Stokes equation, no?
Yes, sí.
Is it possible to eliminate one of the components? Have you think about that? At least in controllability, when we do some kind of controllability of Navier-Stokes equations, we are able to act only if you have three components. In R3, you can control with two components. In R2, you can control with one component of the equation. I don't know
okay,
if
I see
optimal control,
okay.
if it is possible to act
okay. Let me see if I understood. So what you are saying is that if I could choose V star with a smaller number of components.
Yes.
Okay. So let me see if this answer is okay. In the case of the tangential boundary controls, somehow we are discarding a number of components because
yes, of course.
Yeah, so somehow yes, but the number of components is not seen, let's say, in the reference in a Cartesian frame. Somehow we decompose the velocity in some tangential part and some normal part, and we only act with the tangential controls. So somehow we are, in this sense, I think that we are able to reduce the dimension of controls.
Yes, of course. Yes, that's
yeah.
right.
Okay.
Thank you very much. Anybody else? No? Well, I think there are no more questions or comments.
Thank you very much.
Okay, thank you very much, Leonor. That's a pleasure.
Yes.
So see you next month.